Okay, so now we're on to a ramp and pulley question. Okay, so we're going to assume that there's no friction anywhere, not in the pulley, which almost all these questions assume, but also not on the ramp here. Okay, so this just to simplify it, because it's the first one we're going to look at. So the question asks us to find the acceleration of the system and the tension in the rope. Okay, so here is the way that one way that we can approach this. Pretty simple. There's other ways that are a little bit more complicated. So what we do is we draw an imaginary bubble around both of the objects like this. Okay, and we think of this as being one sort of rigid object. Of course, it's going to kind of move, but this rope is not going to stretch, it's not going to bunch up, it's going to move as one continuous object. So we're sort of thinking of it as one object. And this is the line of its motion. So that's what we're interested in. We're interested in forces that act along this kind of, not really a line, but a curve or whatever. So forces that happen inside here, we're not so interested in. Okay, so let's see. This mass is near Earth, so there's going to be a gravitational force acting straight down. So Fg is equal to mg. So that's going to be equal to 50 times 9.8, 490 newtons. 490 newtons pulling straight down. Okay, what else is happening to the system? Well, there's going to be a force pulling it down the ramp. And where is that going to come from? That is going to be a component of the gravity acting on this object right here. So we're going to have a force of gravity acting right there, and it's going to have two components. We're going to think of x and y as being like this, x and y, because we're interested for forces that are acting along this direction here. So it has one perpendicular to that, straight into the ramp, and one straight along the ramp. Okay, so let's call this FGX, and we'll call this one here FGY. Now, I propose that FGY is not really of interest to us. Why is that? Because the object is not moving in this direction. So there must be another force totally balancing this out, which would be the normal force between these two objects. So there is going to be upwards force here, Fn, and these two are going to cancel each other out. Okay, and they're not going to cause motion along this line because it's completely perpendicular to them. So it's not affecting our system's motion. Okay, so this one right here, this FGX, is the one that's pulling us down the ramp. FGX. Okay, lovely. So, oh right, let's go back here and let's just put a few numbers in here. So Fg is equal to m times g, and m is 80. So we have 80 times 9.8, and that's equal to 784 newtons. Okay, great. Now, if I can find it, I think I have our ramp reach on here, because I just want to remind you how these angles all play out when we break these down into components. So this is just our ramp drawn right there. So you can see that Fg is Fg, and Fgx is what we're interested in. So this is 30 degrees right here. This is, side right here is Fg, and this side that I'm interested in is Fg. know that these two are at right angles. Because whenever I break a vector down into components, I always choose components that are right angles. Almost always. So what I need to know about this triangle, I know FG, that came out to be 784. Somehow I need to find out what FGX is, which means I need to know an angle in here. So this is the way I found to figure out what the angle is. That's pretty straightforward. So I just take this line right here and I extend it down. Okay. So these two lines are parallel. So that means that if this angle is 30 degrees, then this angle right here is also 30 degrees. Now I take this gravitational force, so maybe I should stick to my straight lines, and I extend it downwards like that. So that now tells me that this is a right angle. And since this is 30, and there's a little triangle right here, this must be 60. Now, here I have an x, so angles on opposite side there are the same, so this one is also 60. And now I've got an angle up in my big triangle here. Okay, so I can either work with the 60, or I can say, hey, wait a minute, if that's 60 and that's 90, this is 30. So I think I'll stick with the 30 because it's the same as the angle I was given. Okay, so from the 30 degree angles point of view, this is the opposite, and this is the hypotenuse. So that means that the sine of 30 degrees, which is equal to always opposite over hypotenuse, is equal to FGX over hypotenuse is FG. Okay, so if I want to find this component here, FGX, I need to get rid of this FG, so I'll multiply both sides by it. So I'll go FG times FG, cancel out here, and I'll have that FGX, the only thing that's left, is equal to FG sine 30. Okay, so a little bit of geometry is needed to figure this out. So now I know that FGX is FG times the sine of 30. So back here, FGX is equal to FG times the sine of 30. So that's going to be equal to 784, because that's what FG is, times 784 times the sine of 30. Of course, the sine of 30 degrees is 1/2 or 0.5, so I have to take half of this, so that would be 350 and 42, so 392 newtons. Excellent. Okay, so that is going to be right here, 392 newtons. Great. So now I've located the only two forces that are acting along our line. I'll show you, either up the ramp or down over here. So these are the only two forces acting along this line. Now I just pick a direction I think that this is going to go, and it's pretty clear because I've already calculated the forces that we're going to go this way. Okay, and I call all the forces that are pulling me along the direction that I think I'm going to go the driving forces. So over here I only have one, so this is the driving force. and any force that's acting to slow me down, so against the direction I think I'm going to move, I call a retarding force. Okay, this is just giving you a general approach because sometimes maybe you'll have to find this force and you won't know it already, so you won't necessarily know which way your object's going. That's okay, just pick a direction. All the forces that are moving in that direction are the driving forces. All the forces that are moving against that are the retarding forces. Okay. And then the net force acting on the system So it's on the whole system, and that's really important, acting on the whole system is going to be equal to the driving forces minus the retarding forces. Okay, so in our case, it's equal to 490 minus 392. So that should come out to be, let's see, 98 newtons. Okay, so that is the net force acting on the system, F net. Now, if we look back to our question, no one really asked us for that, but they did ask us for the acceleration. And we know from Newton's second law that F net is always equal to m times a. Now, which m are we talking about here? We're talking about the m of the whole system. So assuming that this rope is pretty much massless, we have this m plus that m. Okay, so it's going to be m plus m times a. So it's of the whole system. Okay, so F net 98 equals the whole mass, which is 50 plus 80, so 130 times A. So now in order to solve this, I just have to divide by 130 and divide by 130. Okay, so the acceleration is equal to 98 over 130 meters per second squared.